Okay, so good morning everyone. So last class we were looking at the majority function, and we saw this result due to Valiant which showed that there is a polynomial sized log depth circuit, a monotone circuit which computes the majority function. Okay. And it was an existential result in the sense that we did not explicitly construct a circuit, but we proved that there exists a circuit of log depth polynomial size over and OR gates only, which can compute majority. So what we will do today is, today we will in fact in the next couple of lectures we will look at some basic arithmetic operations such as addition, multiplication, division, powering, and we will try to see their circuit complexity. Okay. So what are the size and depth bound on circuits that can compute these functions. Okay. So let us get started. So the most basic operation of course is addition. So let us define the problem formally. So given two binary numbers, okay, x, which we will assume to be as consisting of the bits xn minus 1, xn minus 2 up to x0, and y, which is similarly yn minus 1, yn minus 2 up to y0. We want to compute x plus y. This is the first problem. Okay. So how do we do this? So I mean, of course this is something that you have seen. So one of the most basic ways to do this is to do using using a adder circuit. Okay. It is also called a ripple adder. So the idea is as follows. So suppose I have these two numbers, right? I mean, this is the way we usually do addition. So we have these two numbers x n minus 1 up to x0 and y n minus 1 up to y0, and if we want to sum them up, we might also have a carry bit somewhere. Okay. So let us say we have a carry bit C0, C1. So this is our, these are our carry bits up to C n minus 1. So C0 of course is 0, and the other bits can take values depending on what x0, y0. So we can actually have individual circuits for each of these operations. Okay. Let us say I have a Ci, I have a Xi, and I have a Yi somewhere. So I can have a circuit for this, and then I can just concatenate these circuits and I can get a formula for addition. Okay. So this is simple to see. So let us say my sum is, let us denote the sum with as z. Okay. Z equal to well, there might be some bit over here. So let us say Zn, Zn minus 1 up to Z0. Okay. So we can write Zi as Xi parity Yi parity Ci. Okay. So this is the formula for Zi. And what is Ci? So, C, or let us say Ci plus 1, or okay, Ci is fine. So, Ci will depend on the previous bits. So, either if both x and y are 1, so xi and yi, so if both of them are 1, then I will get a 1 for the carry bit, or if let us say one of them is a 0, that is let us say xi, sorry, it is I minus 1, x of I minus 1 parity yi minus 1, that is if one of them is a 1, then what should happen? When is Ci equal to 1? When the previous carry bit is a 1. So, and C of I minus 1. Okay. So, this is the definition, and now basically, so these are constant sized circuits. In fact, if you just draw this, this will be a circuit which will have 5 gates, because xi yi is the common gate over here. So, 1, 2, 3, 4 and 5. So, if I just do this for n times, I will get a so concatenating for all I, we get a circuit of size how much? So, we get a circuit of size roughly about 5n, and what will be the depth of the circuit? So, the problem is, so for each I, okay, observe that Zi and Ci depends on Ci minus 1. Okay, so until I get Ci minus 1, I cannot. Okay, so the depth, so the individual depth over here is depth 2. Well, yeah, so I mean you can see here the depth is 2, but then for n levels the depth will be twice n. Okay. And depth equal to 2n. Okay, but this quantity is very large for us, because this is linear, this is optimal. I mean you cannot do better than linear, but the depth is very large. Okay, in this ripple adder circuit. So, the question is, how can we reduce the depth? Okay, how can we kind of do the computation of these carries in a parallel manner. So, here we are, note that here we are doing it in a sequential manner. This is a very inherently sequential circuit. Okay. So, as I said, the question is how to reduce depth. Okay. So, again this is something that you probably would have seen in your computer organization course or somewhere. Okay. So, the next way to do addition is through this algorithm called carry Lookahead adder. So, what does carry Lookahead adder do? So, carry Lookahead adder, it tries to compute, as I said, the Ci's separately. Okay, it tries to compute the Ci's in a parallel fashion. Okay, so how does, so what is the idea? So, the idea behind carry Lookahead adder is, so if you look at this computation, you will observe that of course addition happens from right hand side. So, you will observe that at any point in time, at any instant I, either a carry is generated, a carry bit is generated for the subsequent thing. When is the carry bit generated? If both xi and y are 1, or it is propagated. So, propagated means that it was generated earlier, but now it is being propagated. So, when will it get propagated? It will get propagated if So, if it was, so when I say propagated, I am assuming that it was generated earlier. So, the current Ci is 1. Now, it will get propagated if one of xi or one yi is equal to 1, right. So, that is basically xi parity yi is 1, or it will get cleared. When will it get cleared? That is, the carry bit is set to 0 when both xi and yi are 0. Okay, so, these are the 4 cases. So, this is the idea about the carry look ahead adder circuit. So, at every position either at every position, let us say I, either a carry bit is generated, okay. So, let me see the notation that I have, okay, fine, generated, and that will happen if xi equal to yi equal to 1, or propagated, that is xi parity yi equal to 1. So, this is the same as saying xi and yi equals 1, or cleared if xi equal to yi equal to 0. So, this is the same as saying that xi or yi is equal to 0. So, we will use this idea to create our circuit now. So, let us keep these bits. So, for all I, okay, let us define g of I as xi and yi, and we will define p of I as xi or yi. Okay. The reason I am doing or is because well, if one of them is a 1, then pi is equal to 1, and otherwise pi is equal to 0, and the generate, I mean, if both of them are 1, it is anyway being taken care of by the gi case. Okay. Now, let us look at the what the carry bit is now. Observe that, what did I say, that Ci is equal to 1. So, I have to give a circuit for my carry bit, okay, at any instant I, if and only if and only if what, okay. So, at some index I, my carry bit is 1 if it was generated at some index before I and it got propagated till I, right. So, that is the idea. If and only if there exists some j, okay, j less than or equal to I, such that g j is true, and what else should be true? All the whatever p k's or whatever before I must be true. Okay. So, that is p. So, after j I will have j plus 1, p j plus 2 up to p I. Okay. Just write this properly. So, all of these must be true. Okay. So, this is the definition for Ci to be 1, correct. There exists some j, so I am taking or over all j. So, there exists a j such that this is true and all of these are true. Any questions?
Should that be Ci plus 1?
So, the way we are defining it is Ci plus 1, right. So, right, it will be Ci plus 1, yeah, because we are going up to Pi. Good point. Okay. So, now now if I want to draw a circuit for this, what is the size of this circuit? I mean, if I look at it, so this is the circuit. So, this can be represented by a size order n and depth order log n circuit of Fanon 2, that is a circuit over the De Morgan basis, right. So, I mean, if you actually want to be more precise over here, if you allow unbounded Fanon, okay, that is if you allow an OR gate which can have, or if you allow an AND gate which has like Fanon as large as possible, and if you allow an OR gate which has Fanon as large as possible, then note that this can be done by just a depth 2 circuit. You need just one AND gate with all these gates feeding into it, and you need just one OR gate with all these gates feeding into it. And how much I mean, how do you compute these Gj's and Pj's? So, that is given exactly over here. So, these are the inputs xi and yi's. So, using this you can anyway compute, okay. So, basically by a depth 4 circuit of unbounded Fanon, you can compute any Ci, right. But if you want to have bounded Fanon, that let us say if you want to have Fanon 2, then I will just expand this out into a tree, and I will get a circuit of depth order log n with Fanon 2, right. But the, depth 4 because so here I have depth 2, and for each Gj and Cj I have one more depth. So, depth 3 actually. Okay, so here I have another additional depth, right, because I have to compute these Gi's and Pi's, okay, below it, right. Okay, and once I have the Ci's, then I can directly implement this function and I can get it. So, basically with unbounded Fanon I have a constant depth circuit, and if I have bounded Fanon then I will have a log n depth circuit, but what will be the size of the circuit computing addition? So, this is basically the size of the circuit computing the carry bit. Now, I have to implement it to compute my complete addition, that is I have to compute Z. So, what will be the total size? The size. So, for each Ci I have order n, right, because I will have So, it will be order of n square now, the size will be order of n square because I have to compute n many carries, right. Yeah. So, the depth is order log n. So, size to perform addition will be order of n times n. So, it will be order of n square, and depth will still remain. Order log n. So depth is in fact optimal. You cannot do better than log n. Okay, you cannot. So if you are if you only allow bounded fan in, you cannot do better than log n, because if you allow bounded fan in and if you are smaller than log n, then you can't even see the entire input. Okay, so this quantity is optimal, right? And we saw that, well, there are circuits of size linear, right? So this quantity is not quite optimal. Okay, so the question is, can I have a circuit which has like best of both the worlds? I mean, which is of depth log n as well as size linear with bounded fan in, right? So that is the question which arises. So here, of course, we are reducing the depth, but the size increases. Okay. So clear? Okay. So this brings us to the third mechanism of computing or of performing addition.